Hi everyone, welcome to this video where we are going to discuss about one of the error correction methods called as hammingcode. So you know that we have discussed quite a few error detection mechanisms, which include your CRC, LRC, VRC, and 2D parity check and also checksum. So in this video, let's touch what do you mean by error correction and how we can achieve error correction through hammingcode. Okay. So first things first. So why should I bother about detection when I can do error correction? Because everyone feels that error correction might be the best way to handle errors. Because in case of error correction, the receiver will be capable enough of identifying the bit positions. Thereby, you can flip the bits back to its original data and reduce the burden by not making the sender to retransmit the data. So error correction looks a better option, because as I told you, it's efficient for the receiver to detect and correct the error without the need for the retransmission by the sender. So let us say that if you don't have a big idea, error correction looks really good. But the fact is that error correction is more difficult than error detection. Why? Because it's straightforward. In case of detection, just identifying whether an error occurred or not is enough. You need not bother about the number or the type of errors. You need not bother about how many errors happened or where the bit positions the error has happened. You need not bother. You can simply identify the errors and say whether there are any errors or not. That's all. But that is not the same case for error correction. In case of correction, the number of errors and their precise location in the message needs to be identified. So you have to find out how many bit positions came as an error, and also which bit positions have generated this error, or at which locations in your message did the error happen. So the number of errors and the size of the message are important factors. To put it into perspective, just look at this. For an 8-bit message with 1-bit error, and in order to correct it, 8 possible locations should be considered. So the error might have happened at any of those 8 locations. To correct 2 errors in the same message, the permutations now have become 28 possibilities. Consider a message of length 10,000 bits and maybe a burst error of 10 bits. Imagine the complexity the receiver has to face in order to provide error correction. So error correction is a technique which can be implemented only in case if you know that the error rate is very high, like long distance communications or satellite communications. Whereas for your local area networks and other wired connections, error detection should suffice. Now, let us talk about one of the prominent codes that we use for error correction, which is also called as a Hamming code. The other name for the Hamming code is called as, or is given as, forward error correcting or FEC codes. You can see here, this is what forward error correcting or FEC codes. These are a family of linear error correcting codes that uses redundancy to correct a single bit error. Around 1947, he is the great man. The Richard W. Hamming developed a technique for detecting and correcting single bit errors in transmitted data. His technique requires that 3 parity bits or check bits be transmitted with every 4 data bits. So that is the reason his algorithm is given a name called as 7,4 code, which tells you that the total message transmitted is 7 bits for a actual data bits of 4 bits. As I said, because it requires 7 bits to encode 4 bits of data. So this is his original Hamming code. Now, if you see here, the Hamming distance between 2 words of the same size is the number of locations in which their respective bits differ. So in order to explain it in a better manner, let me show you. So the Hamming distance between 2 words x and y is represented using as d of x and y. Now these are the 2 code words. The Hamming distance is nothing but the number of bit positions that differ in these 2. Check out the first bit position, 0. There is no change. But second bit position, there is a change. The third bit position is a change. Fourth, there is no change. And fifth, there is a change. So how many changes have happened between these 2? These 2 code words differ in 3 bit positions. So the Hamming distance is 3. Similarly, now if you're given a long sequence of binary data and not to compute your Hamming distance, the best way is to do is to perform exclusive OR of that particular data and calculate the number of ones. So check out this example. I am given once again two code words 10101, 11110. Okay. Now, in order to find out how many data bits or what is the Hamming distance between these two code words, what I can simply do is perform an exclusive OR, and this is my answer, and then count the number of ones in this answer. You can see the number of ones is 3. So if you are given in a long sequence of code words, and in order to compute the Hamming distance, simply perform an exclusive OR and then count the number of ones, which would be an easier way. Because if you start counting like this, you might get confused and there is a chance of making a mistake. Now, in a set of code words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs of code words. Now, what is this minimum Hamming distance? I'll show you with an example. Now, if our system, if you have different code words, the minimum Hamming distance is the distance between any two legal code words. Of all the possible combinations of code words, the minimum Hamming distance is the least distance between any two legal code words. Usually, we represent the minimum Hamming distance using dmin. Now, if our system is to detect up to d errors, the minimum distance between the valid codes must be d minimum is equal to d plus 1, so that the received code word does not match a valid code word. In order to understand this better, check out this example. A code scheme has a Hamming distance of d minimum is equal to 4. Okay, this code guarantees the detection of up to how many errors? 3 errors. How did you get this 3 errors, sir? D minimum is given as 4, and if you put 4 here, and how many errors I am going to detect? D. So you take plus 1 to this side. D is equal to 4 minus 1, that is equal to 3. Okay, so the D minimum, the minimum distance of the minimum Hamming distance in order to detect D errors is given as D plus 1. Similarly, because we are talking about an error correction scheme, that to guarantee correction of up to T errors, in all cases, the minimum Hamming distance in a block code must be D minimum is equal to 2T plus 1. What is it? 2T plus 1. Okay. Now, let me show you. This is another example which I got from the internet, which was asked once upon a time in the GATE exam. So consider a binary code that consists only 4 valid code words as given below. So these are the 4 valid or legal code words, and let the minimum Hamming distance of code be P, and the maximum number of erroneous bits that can be corrected by the code be Q. Calculate the value of P and Q. Now, first let us talk about P. He is asking the minimum Hamming distance of any of these code words is P. So first let me calculate the minimum Hamming distance between first and second. If you see, there is 5 zeros here and I have 3 ones here. So between the first and second code word, the minimum Hamming distance is 3. What about first and third one? Once again, it is 3. What about the first and fourth word? So zeros, once again, it is 4. So how did I get this? You simply count the number of ones. That's all, because these are all zeros. Now, similarly, I have to check for all possible code words, right? Now I am going to check for second and third. What is it? So 0, 1, 0, 1, 1. So 1, 2, 3, 4. There are 4 bit positions that differ in value. So it is 4. What about the second and fourth? 0, 1, 0, 2, 3. It is 3. Similarly, you have to calculate the same for your third and fourth code word also. What is the minimum Hamming distance between these two? So 1, 2, 3. So the answer for P is nothing but the minimum Hamming distance between any two legal code words. If you look at the values, the P value is 3. Now, once I have the minimum Hamming distance, which is D minimum is equal to 3, I need to find out the maximum number of erroneous bits. Or in other case, I have to put it into this formula. I have 3 now, and I need to find out what is the value of t. So 3 is equal to 2t plus 1, because t designates the number of errors that you can guarantee correction of. Okay, so you need to guarantee the correction of the t errors. So in that case, so here, which gives me the value of t is equal to 3 minus 1 by 2, which is nothing but 1. So here the value of q will be, or this q is equal to 1. So p is 3 and q is 1. P is equal to 3, which is nothing but the minimum Hamming distance between any of the two code words, whereas q is nothing but the maximum number of errors that you can correct with this particular code. So this is how you calculate using these two formulas. Now, there is another example. If we want to be able to detect 2-bit errors, what should be the minimum Hamming distance? So for this, it is also pretty simple. Once again, we studied the formula d minimum is equal to, I wrote it here, s plus 1. So he's asking me, in order to detect 2-bit errors, so s is equal to 2. So 2 plus 1, what is the d minimum? It's a straightforward answer, which is equal to 3. The minimum Hamming distance in order to detect 2-bit errors is 3. So this is how you calculate the minimum Hamming distance which is required in code words in order to detect and also correct some number of errors, maybe by s or t. Okay, now let me carry on to the next part, where how you generate a Hamming code. In the Hamming code, the number of redundant bits to be used is dependent on the number of message bits. So how many bits do you use? Usually we use a generalized version of the 7,4 model proposed or given by Richard Hamming. Now let m be the number of message or information bits. Then the number of redundant bits r, which is required for generating the Hamming code, is determined using the formula 2 power r greater than or equal to m plus r plus 1. Okay, that is what we got. Now, as I told you, if you want to understand this better, it is always easy to take the numerical example. Now, for example, consider a data unit consisting of 7 units, which I'm saying that m is equal to 7. Okay, to implement error correction using the Hamming code, the number of redundant bits required is calculated using the above formula. So I have to substitute here 2 power r greater than or equal to, what is m? 7. So 7 plus r plus 1, which gives me an equation 2 power r greater than or equal to 8 plus r. Now you start from 1. 2 greater than 8, no. 2 square, 4 greater than 10, no. 2 cube, 8 greater than or equal to 11, no. 2 power 4, you just take the random values starting from 1. Now when you come to 4, 2 power 4 is 16, greater than or equal to 8 plus 4, 12. So if you put r is equal to 4, you get the equation 16 greater than or equal to 12, which is true. So because r is the minimum value which satisfies the equation, I select r is equal to 4. Sir, what is this r? R is nothing but the number of redundant bits that are needed in order to provide single error correction using Hamming code. So now the total number of bits in the sent code word will be a total of 7 plus 4, which is nothing but 11 bits. You understand? 7 is your message bits. 4 is the number of redundant bits that you just calculated. Okay. Now let me take it a little bit further. Where are these redundant bits placed? In CRC or in checksum, what we usually did was we appended the parity bits towards the end of the message. It's a little bit different in case of Hamming code. You do not add the entire redundant bits at the end or at the beginning. These redundant bits are also placed within your message or within your data words. I'll show you how. Usually, once you decide the number of redundant bits that you need to use, these bits or these redundant bits occupy the positions or occupy the bit positions of powers of 2. That is 1, 2, 4, 8, 16. Now, you know that a message that is to be sent is now consisting of 11 bits. Your code word consists of 11 bits, right? So just draw a table which consists of 11 bits here. Okay. And in these 11 bits, what we need to do is you need to write it down. So this is my table which consists of the 11 bits here. And how many redundant bits I need? 4 redundant bits, right? These 4 redundant bits occupy the position of powers of 2. So this is 2 power 0, this is 2 power 1, this is 2 square, and this is 2 square, and this is 2 cube. So these are the 4 bit positions which your redundant bits occupy. The remaining bits is occupied by your data bits. So we have a total of data bits is equal to 7, the number of total data bits. So redundant bits is equal to 4, which makes the total code word length to be 11 bits. Okay, so this is how. Now let me take a numerical example and show you how do you calculate the Hamming code if you are given a data bit or if you are given a data word. Okay, so this is how. The first thing that you need to remember is, first you need to calculate the number of redundant bits that are required. After calculating the number of redundant bits that you require, you draw a table and place the redundant bits in the bit positions of powers of 2. Okay, now the redundant bits are calculated based on the message bits according to their positions. So R1 is calculated using 3, 5, 7, 9. You see, I have written all the bit positions over here. R2 is calculated using message bit positions of 3, 6, 7, 10, 11. R4, that is your third redundant bit, is calculated using message bit positions of 5, 6, 7. R8, 9, 10, 11. So these are the 4 bit positions. Now these same redundant bits are occupied in these positions. Now let me take a numerical example. As I just told you, calculate the Hamming code for the data word. So this is my given data word. How many bits are there? 1, 2, 3, 4, 5, 6, and 7, right? So a total of 7 bits. Now we just calculated that in order to transmit 7 bits, I require 4 redundant bits, right? We just calculated that, which makes my total message length of 11 bits. And I have written the 11 bits like this in a table. And I have already wrote down the 4 redundant bits in their corresponding positions of powers of 2. 2 power 0, 2 power 1, 2 square, and 2 cube. The remaining data bits occupy the remaining boxes. So 1, 0, 0, 1, 1, 0, 1. I just did nothing. I just simply wrote down the given message bits in their particular positions, and I kept the redundancy bits. Now, in order to send this code to the receiver, I need to find out the value of R1, what is R2, what is R4, and what is R8, and then place those corresponding bits in these positions and then send it to the receiver. For that, I have a small trick up my sleeve, because sometimes I found a little bit difficult to remember all these bit positions. So once I draw this table, what I usually do is, the remaining parts or the remaining bit positions, I'll simply break them up as sum of the powers of 2. So 3 is written as 1 plus 2, 5 is written as 1 plus 4, 6 is written as 2 plus 4, 7 is written as 1 plus 2 plus 4, 9 is written as 1 plus 8, 10 is written as 2 plus 8, 11 is written as 1 plus 2 plus 8. So why you did that? Because now when I start calculating R1, what I can simply do is, whichever bit positions have 1 here, I'll simply note them down. So 1, exclusive 1 plus, and there is a 1 here again, 0 plus, and there is another bit position 1 here. So what is the value? I'm simply writing it down. Plus, there is another 0 here because I have 1 here, and finally I have another 1 here. I'll write out 1 here. You simply need to perform an exclusive OR here, or in other ways, one more thing is just perform an even parity. So 1, 2, 3 to become even, simply place a 1 here. That's all. Similarly, go for R2 also. R2, whichever bit positions have got 2 in the sum, just write them down here. So for R2, search for 2. There is 2 here, so 1 plus. There is another 2 here, the bit position is 1 plus. There is another 2 here, so 1 plus. There is another 2 here, 0 plus. There is another 2 here, bit position is 1. So what is the value of R2? So 1, 2, 3, 4. Even parity 0. What about R3 or R4? The third redundant bit. Simply write down the positions wherever you have 4. So 0 plus, another 4 here, 1 plus, another 4 here, 1 plus, that's all. So once again use even parity 0. 1 plus, there are already 2 ones, which is even. So you simply put a 0 there. The last redundant bit is your R8. So just simply note down the bit positions wherever you have 8. So 0, 0, 1. So 0 plus 1, which gives me, once again, go for parity, 1. So now you have these bit positions. So R1 is to be written as 1, R2 is written as 0, R4 you calculated as 0, R8 you calculated as 1. So now the actual code word transmitted is, tell me, read it back to me, 1 0 0 1 1 1 0 0 1 0 1. How many bits? 11 bits. Calculate 3 6 8 11. So these are the 11 bits that are actually transmitted to the receiver. So let me give you another example so as to get a better idea. Okay, let me do another example. Now in this example, once again, I'm given a data word which is of 5 bits in length. So you have to implement the same formula. So in this formula, what I will get is 2 power r greater than or equal to m is 5 here, because I'm given 5 bits of data. So 5 plus r plus 1 gives me 6 plus r. The same way, start your count from 1. So 2 greater than 6, no. 2 square, 4 greater than 6, no. 2 cube, 8 greater than 9, no. So once again, you will get r is equal to 4. So which makes the total length of the code word that is to be transmitted is 5 message bits plus 4 redundant bits, which gives me 9 bits. So once again, I draw 9 boxes here, and these 4 redundant bits occupy the bit positions of your powers of 2. So 2 power 0, you can hear 2 power 0, 2 power 1, 2 square, and 2 cube. So these are the redundant bits which occupy their respective positions of powers of 2. Now to calculate this, start the same way that I did, R1. So just look for wherever 1 is here. So 1 plus, tell me what is what? Tell 1 plus 0 plus 1 plus 1. Perform an even parity, 1 2 3. So just write 1 here. What about R2? Check out for where it is 2 here. So there is always a sum 2 here. So 1 plus, there is no 2, 0 plus 1 plus, that's all. Okay, so give me a second. Let me just wipe this last one off. Okay, and so which is equal to 0, even parity. So let me calculate R4. R4 is equal to, tell me what is what? R4, 0 plus 0 plus 1, which equals to 1, because it's an odd parity. I have only a single one which is odd, so I simply add a 1 here. R8 is equal to, there is no other value, so 1. So which makes my transmitted data is 1. If you want, if you are getting confused, you can write ones here also, so that when you read back the data, it will be much more easier for you and you won't make any mistakes. R2 is equal to 0, R1 is equal to 1. So 1 1 1 0 0 1 1 0 1. This is the actual data that is transmitted from the sender to the receiver using a Hamming code. Now I have been discussing about how to generate the Hamming code, but what it actually does, how does it provide the error correction? Let's check that out. Now let's consider as an example here. So this is another example that I have taken. So this is the actual data. So 1 1 1 0 0 1 1 0 1. So I purposefully placed an error to the receiver. Let us assume that the receiver has received with 1 error. But how does it know that it is an error? So once the data is received at the receiver, what it will do is it will perform the same calculation of the redundant bits, because it knows where the redundant bits are, how many redundant bits are used, and their bit positions. Once again, let me calculate R1 here from the received data. So R1, 1 plus 0 plus 0 plus 1, which gives me 0. R2 is equal to, calculate R2 also from there, from the received data. So 1 plus 0 plus 0 plus 0. Now what do I get here? 1. What about R4? Let me calculate for R4. So R4 it is here 0 plus 0 plus 0, which is nothing but 0. What about R8? R8 is equal to, simple, straightforward. It is only one bit position. It's 1 here, 1. So if you compare, you know that the received R1 is 1, but when you calculate, you got R1 as 0. So R1 is a mistake. R1 contains an error. Okay. Then R2, you got 1 and you have a 0 here. Once again, R2 is also containing an error. And what about R4? R4 you calculated as 0, but you have 1 here. R4 is also a mistake. What about R8? R8 is the same. Now you have to look for the bit position where these 3 redundant bits match. In simple terms, 1 plus 2 plus 4. Where we have it? Which is nothing but 7th bit position. So you identify whatever value is there in the 7th bit position, you change it, you flip it. So automatically by flipping the 7th bit position, the receiver will get the data as 1 1 1 0 0 1 1 0 1, which is the same as the data that is transmitted. So this is how error correction is done. Now here I didn't do anything. I just sent the data. I purposefully created an error, but still the receiver is able to detect the bit position and then flip that particular bit, because if it's a 1, then go for 0. If it is a 0, then go for 1. That's all. So this is how error correction can be made. So let us try one more example just to get ourselves used to how it is made. Now I actually made an error in this particular bit position. So in this case, once again the receiver does everything. It will calculate R1. So let us try with me, do it with me. 1 plus 0 plus 1 plus 1, which is nothing but 1. R2 is equal to 1 plus 0 plus 1, which is nothing but 0. R4 is equal to 0 plus 0 plus 1, which is nothing but 1. R8 is equal to 1. So if you see, R1 does not have a mistake or does not have an error. R2 does not have an error. R4 does not have an error. The only bit position containing error is R8. R8 is actually taken from the message position, this one. So you simply change this R8 bit. You have to simply change the R8 bit. That's all. So this is how you actually get the particular thing, because this 8th bit position is only repeated here, in this position. So you only change this particular one. If R1 is also a mistake, then you can change R1 plus, if both R1 and R8 are coming as a transmission error, then you have to change this bit, because only R8 came as a mistake. You know that the bit position which has made a mistake is number 1, or is this particular bit position. You flip it to 1, then you will get your original data. This is how Hamming code is used to detect and correct single bit errors. Okay. So thank you very much for watching. I'll try to give even more numerical examples in the next video, which I make on Hamming code. So till then, take care. Once again, if you like the videos, please share and subscribe. Thank you very much. Do take care.